All right, welcome back to the deep dive. Today we're doing something, well, a little bit different. We're going to, try to think like philosophers today, really put those mental gears into
I
overdrive.
like it.
And our guide for this philosophical workout is going to be one of the all-time greats, Rene Descartes.
Yeah, can't go wrong with a little Descartes.
No, absolutely not. We're going to be diving into his methods, his approach to knowledge, how he tried to figure out what's true, how we can be certain about things.
Right, yeah, I mean, this isn't just about learning about Descartes, right? This is like taking his way of thinking, his methods, and seeing if we can apply it to our own lives.
Exactly. So think of this as like, I don't know, like a mental boot camp or like a toolkit, to help you sharpen your thinking no matter what you're doing.
Yeah.
Whether you're, I don't know, preparing for a big presentation at work or just trying to learn something new.
Yeah, love that. And our source material for this little deep dive, our intellectual playground, is going to be the Stanford Encyclopedia of Philosophy's entry on Descartes' method.
Yeah, fantastic resource. Really comprehensive, but also pretty easy to understand, which is, always helpful.
Right. And what I find really fascinating about this entry is how much detail it gives us about how Descartes actually intended for us to, think and inquire. It's not just about, I think, therefore I am. It's about a whole system. Like this is his step-by-step guide to achieving like intellectual certainty, which is, something we can all use a bit of in this day and age.
Absolutely. Yeah, that's a great point. It's more than just that one famous quote. It's a whole framework for approaching knowledge and figuring out, what we can really be sure of.
Right.
So our mission today, I think, is to really get under the hood of this method, to understand the nuts and bolts of how he built his arguments, how he went about building this certain and evident knowledge. And believe me, there's a lot more to discover here than you might think.
Oh, absolutely. There are some really fascinating and sometimes surprising elements in Descartes' thought. So, to start thinking like Descartes, to really get into his mindset, we should consider the context, the intellectual world he was operating in.
Right. Yeah, of course. Every great thinker is shaped by their environment.
Yeah.
So what was happening at the time that might have influenced Descartes' approach to philosophy?
Okay, so picture this. Europe is in the midst of this huge intellectual shift, right? This movement away from the traditional Aristotelian philosophy that had dominated, Western thought for
Right,
centuries.
yeah, Aristotle, the big guy, the OG philosopher. So what was Descartes' issue with Aristotle's views? What made him want to break away from that tradition?
Well, Aristotle had this huge influence on how people viewed the world, right? His ideas about physics, about nature, they were like the accepted truths for a long time. But Descartes was drawn to something different. He wanted to create a unified approach to knowledge, one that combined things like mechanics, physics, and mathematics.
Oh, yeah, interesting. But wasn't Aristotle himself a bit wary of mixing those disciplines? I seem to remember something about that from my philosophy classes way back when.
You're right, yeah. Aristotle did warn against blending different fields too much. He thought they each had their own distinct methods and principles. But there were these other thinkers, people like Isaac Beeckman, who Descartes met in 1619, who were really interested in exploring this intersection between math and physics.
Right, so they were pushing the boundaries, trying to find new ways to understand the world.
Exactly. And they had this term for it, physico-mathematics, which sounds a bit clunky, I know, but it captures this idea of using the precision of mathematics to study the physical world. And this was a huge influence on Descartes. It really sparked his own desire to find a more rigorous and, more importantly, a more certain foundation for knowledge.
So he's encountering this physico-mathematics, this blend of different fields. And how does this begin to shape his own method, his way of thinking like a philosopher?
Right, so around the 1620s, while he's grappling with these new ideas, Descartes starts working on this really important text called Rules for the Direction of the Mind.
Rules for the direction of the mind, that sounds pretty central to his whole project, his whole approach.
It is. It really is. It lays out, the core of his methodological thinking, the most detailed account we have of how he believed we should, well, direct our minds towards truth.
A philosopher's guide to thinking. Sounds like required reading for this deep dive.
Absolutely. Though it's interesting, this work was never actually finished. It remained unpublished during his lifetime, and he never even really mentioned it in his other writings or letters. It's like this hidden treasure trove of his thought.
Wow, so this is like the lost scrolls of Descartes, right?
Yeah.
The behind-the-scenes look at how he developed his ideas. So getting down to brass tacks, how does he define method in these rules?
Okay, so in Rule 4, he defines it as a set of reliable rules which are easy to apply. Now, you might be thinking, well, duh, isn't that what any method is? But for Descartes, this wasn't just any old set of rules. He was aiming for something much more powerful, a set of rules that could, if followed precisely, lead you away from falsehood and progressively build your knowledge. He believed you could actually reach a true understanding of, well, everything within the reach of human intellect just by following these rules.
Reliable and easy to apply. That sounds like a pretty good sales pitch, honestly.
Yeah.
So how did he structure these rules? How did he organize them in the rules?
He divided them into three main sections. The first part, rules 1 through 12, focuses on defining science, what it actually is, what it means to have scientific knowledge. And he also introduces his core operations, intuition, deduction, and enumeration, and these simple propositions.
Simple propositions. Okay.
Mhm.
What are those exactly?
Basically, they're those self-evident truths, those things we know for sure with absolute certainty, like a triangle has three sides, or 2 plus 2 equals 4. Simple things like that, but things that are absolutely undeniable.
Right, those fundamental truths that we kind of just know intuitively. So he's starting with the most basic, most certain knowledge and then building from there.
Exactly. And then the next section, rules 13 through 24, deals with what he calls perfectly understood problems. These are problems where you know all the necessary conditions for a solution, things like problems in arithmetic and geometry. And then the last part, rules 25 through 36, was supposed to tackle those really complex, imperfectly understood problems, problems in natural philosophy, metaphysics, the big, messy questions where you don't necessarily know all the conditions or all the variables. But, like we wanted before, the rules cuts off at Rule 21, so we don't have his complete take on those trickier problems.
Right, so we only get a partial view, but still a valuable one. So we've got these three sections, each dealing with a different level of complexity. It seems like there's a real emphasis on building knowledge systematically, step by step. So let's dive into those core operations, intuition, deduction, and enumeration, which to me sounds like, the heart of his method.
Absolutely. Those are the tools he uses to build up knowledge from those simple propositions to something much more complex.
So where do we start? What's step one in thinking like Descartes?
Well, we start with how he redefines science itself. In Rule 2, he states that science is certain and evident cognition. Now, many Aristotelians would have actually agreed with him on this definition, but here's where things get interesting. Descartes didn't believe that all the sciences could achieve this certainty equally.
So he's setting a higher bar for what counts as true knowledge, right?
Exactly. You see, the Aristotelian view allowed for probable cognition, especially in natural philosophy. But Descartes wanted something more, something stronger. He straight up rejected anything that was merely probable, those kind of wishy-washy conclusions. He said, and I'm paraphrasing here, but he basically said, we should only believe what is perfectly known and can't be doubted. Boom, mic drop.
So he's all about certainty, no room for maybes. Bold move.
Right. And this is where intuition comes in. This is how he believed we could actually grasp those certain truths.
Okay, let's talk about intuition. We use that word all the time, but I have a feeling Descartes has a very specific definition in mind.
Oh, you bet he does. In Rule 3, he goes to great lengths to distinguish his definition from our everyday, casual use of the word. He says, by intuition, I do not mean the fluctuating testimony of the senses or the deceptive judgment of the imagination, but the conception of a clear and attentive mind, which is so easy and distinct that there can be no room for doubt about what we are understanding.
Okay, so it's not just gut feeling or a hunch. It's about clear and attentive thinking.
Exactly. It's like the sudden flash of intellectual insight. So clear, so undeniable, that it carries its own certainty, its own evidence within itself.
Clear and attentive mind, easy and distinct, no room for doubt. Sounds like a pretty high standard for knowledge.
Yeah.
Can you give us some examples, from Descartes himself to illustrate what he means by this kind of intellectual seeing?
Sure. He gives a few key examples in the text. He says things like that he exists, that he is thinking, that a triangle is bounded by just 3 lines and a sphere by a single surface. So notice how these examples include both contingent truths, things that just happen to be true, like I exist right now, and necessary truths, things that must be true by their very nature, like the properties of a triangle or a sphere.
Right, so it's not just about abstract geometric shapes.
Yeah.
It's about even our basic awareness of ourselves as thinking beings.
Precisely. And he sees this intuition as a kind of intellectual seeing, like you're directly apprehending something with your mind. It's not about relying on definitions or just sensory information. It's about seeing the thing itself in all its clarity directly with your mind.
This is fascinating. So we're talking about this direct mental grasp of truth, this immediate clarity. And what exactly are we seeing with our minds during these moments of intuition? What are these things that we're directly apprehending?
The objects of intuition, according to Descartes, are what he calls simple natures. These are like the fundamental building blocks of our knowledge. They're not complex ideas or propositions, but these basic, indivisible notions that are so clearly and distinctly known that they can't be broken down any further. Think of them like the atoms of thought, the simplest units of knowledge.
Atoms of thought. Okay, so what are some examples of these simple natures?
He divides them into three categories: intellectual, material, and common. Intellectual simple natures are things like, knowledge, doubt, volition, basically, the activities of our minds. Material simple natures are, the basic properties of physical things, things like extension, shape, motion. And common simple natures are those that apply to both mind and matter. Things like existence, unity, duration, and those fundamental logical principles like things that are equal to the same thing are equal to each other.
Okay, that makes sense. So intellectual simple natures are about our minds, material ones are about physical stuff, and common ones bridge the gap between the two.
Exactly. And he believed that all human knowledge, ultimately, is built up from understanding how these simple natures combine and interact. It's like these simple natures are the ingredients, and all of human knowledge is the recipe book.
Interesting analogy. So we start with these simple natures, these basic truths that we grasp through intuition. But how do we go from there to building more complex knowledge, to understanding the world around us? That's where deduction comes in, right?
You got it. So, right after he introduces intuition, in Rule 3, he defines deduction as this: the inference of something as following necessarily from some other propositions which are known with certainty, provided they are inferred from true and known principles through a continuous and uninterrupted movement of thought in which each individual proposition is clearly intuited.
Whoa, that's a mouthful. Can you break that down for us?
Sure. Basically, deduction is like building a chain of reasoning. Each link in the chain has to be connected to the previous link through a clear and certain intuition. And the whole chain needs to start from a solid foundation of those true and known principles.
So it's about building a logical argument where each step is supported by an intuition.
Right. It's not just about jumping to conclusions, but about creating a series of carefully connected steps, each one supported by its own little flash of intellectual insight.
That makes sense. So we're not just guessing, we're building a case, step by step. And what about those steps themselves? Can you give us an example of how deduction works in practice?
He gives a couple of helpful examples in Rule 12. One is about the relationship between extension and shape. He says that when we deduce that nothing which lacks extension can have a shape, we're basically seeing intuitively that shape requires something to take up space, to have extension. The other example is about Socrates. He says that if Socrates doubts everything, then it follows that he must understand what it means to doubt, to distinguish between truth and falsehood.
Okay, so we see the connection between shape and extension, and the connection between doubting and understanding truth and falsehood. These are things that must be true based on how those concepts are related.
Right, and this is a key difference from how we often think about deduction in everyday life. For Descartes, each step in a deduction is itself a kind of intuition. It's a sequence of clear and distinct perceptions.
So deduction is like a series of mini intuitions, all linked together in a logical chain. And I know he was pretty critical of the Aristotelian syllogism, which was a standard form of logical reasoning at the time. Why was that?
Yeah, he wasn't a big fan of syllogisms. You see, the validity of syllogism depends only on its form, the structure of the argument, not the content of the premises. For example, you can have a syllogism like, all cats are mammals, all mammals are animals, therefore all cats are animals. That's a valid syllogism, right? But the problem, according to Descartes, is that you don't really gain any new knowledge from this. You're just restating what was already contained in the premises.
So he felt like syllogisms were kind of just shuffling around information rather than discovering something new.
Exactly. He wanted a method that could lead to genuine discovery, to uncovering new truths about the world.
And that's where his method of deduction shines, right? It's not just about rearranging what we already know, but about building new knowledge through a series of insightful connections.
Right. He wanted to create a method that could extend to the discovery of truths in any field whatever. He wasn't content with just analyzing existing arguments. He wanted a tool that could actively expand the boundaries of human understanding. So, to recap, we have intuition, which is like a direct grasp of basic truths, those simple natures. Then we have deduction, which is about building a chain of reasoning from those intuitions to arrive at more complex conclusions. So, what's the deal with enumeration? Where does that fit into this whole
Right,
process?
that was the third core operation I remember.
hmm
And honestly, it always seemed a bit mysterious to me.
Well, think of it like this. Enumeration comes into play when your deductions become really long and complex. Our minds can only hold so much information in a single intuition, right?
Yeah, I can barely remember my grocery list sometimes. So enumeration helps us deal with those really intricate arguments that would otherwise overload our mental circuits.
Exactly. It's like a technique for expanding the scope of our intellectual vision. Sometimes you have these arguments where the chain of reasoning is so long and complex that you can't just hold the whole thing in your mind at once. That's when you need enumeration to break it down into manageable chunks.
So it's about making sure we don't get lost in the weeds when we're dealing with those big, complex problems.
Right. And the source mentions that there are actually 5 different senses of enumeration in Descartes' system, each with its own specific function. It's more than just a single technique. It's like this multi-layered approach to ensuring that our reasoning is rigorous and thorough.
Okay, so it's not just about counting things, but about strategically managing complexity. I'm intrigued. What are these 5 senses of enumeration?
Yeah. Okay. So the first one, enumeration one, is about verification. Like after you've done a deduction, you go back and double check each step, each connection to make sure you haven't made any logical missteps. It's like double checking your math homework.
Right, making sure you haven't missed a sign or anything. Got it.
Yeah.
What about enumeration 2?
Enumeration two is more about planning your attack. Before you even start deducing, you use this to break down a complex problem into smaller, more manageable parts. You figure out which parts are the most fundamental, which ones you need to solve first, and then you work your way up from there. It's like outlining a paper before you start writing it.
So you're creating a roadmap, a plan of attack.
Exactly. And then we have enumeration three. This one is actually a form of deduction itself. It involves systematically considering all the possible alternatives or similar cases related to a claim.
So you're looking at the problem from every angle, trying to cover all your bases.
Right. A prime example of this is Descartes' method of universal doubt in his meditations. He systematically doubts everything he thinks he knows, trying to see if there are any possible reasons to reject even his most basic beliefs. It's like he's stress testing his knowledge, trying to find its breaking point.
Interesting. So doubt as a tool for finding certainty. What about enumeration 4?
Enumeration 4 comes in handy when your conclusion is based on a whole bunch of different pieces of information rather than a single linear line of reasoning. Like imagine you're trying to solve a jigsaw puzzle. You don't just start with one piece and go from there. You look at all the pieces, you try to see how they fit together, you group them by color or shape.
So it's about piecing together a complete picture from a bunch of seemingly unrelated bits of information.
Exactly. And then we have the final one, enumeration 5, which he actually refers to as induction.
Induction. Wait, isn't that the opposite of deduction? How does that fit into his system, which seems so focused on finding certainty through logical reasoning?
Yeah, this one is a bit tricky. Basically, induction is about inferring a general rule from specific observations. Like if you observe that every time you drop an object, it falls to the ground, you might induce that all objects fall when dropped. But for Descartes, even this kind of inductive reasoning should ideally be a stepping stone towards a deeper, more certain understanding that can be achieved through deduction from first principles. It's not just about noticing patterns, but about explain why those patterns exist.
So even when we're observing the world around us, the ultimate goal is to connect those observations back to a solid foundation of logical reasoning and clear and distinct ideas.
Exactly. So we've got our 3 core operations: intuition, deduction, and enumeration. These are the tools that Descartes uses to build up his knowledge. And to really see how this works in practice, let's look at a concrete example: his work on the anaclastic line.
Okay, the anaclastic line. Now we're getting into the nitty-gritty. So what was this problem all about, and how did he approach it using his method?
So the problem of the anaclastic line was a geometrical problem, a tough one. Basically, it's about finding the exact shape of a lens that will focus all parallel rays of light to a single point, like a magnifying glass.
Right, so a pretty practical problem with implications for optics and lenses.
Exactly. And Descartes considered this to be an imperfectly understood problem, one where you don't have all the information up front. So his approach, as he describes in Rule 8, was to use enumeration 2 to break down this complex problem into a series of simpler problems. He basically created a plan of attack, a sequence of questions, starting with the ultimate goal, the shape of the lens, and then working back to more fundamental questions about things like the nature of light, the laws of motion, how light interacts with different materials, and so on.
So he's creating a sort of reverse engineering plan, starting with the desired outcome and then figuring out the steps needed to achieve it.
Precisely. And the key here is that he aims to solve each of these simpler problems first, using intuition and deduction, and then use those solutions as building blocks to figure out the solution to the original, more complex problem.
So it's like solving a bunch of mini puzzles and then putting those pieces together to solve the bigger puzzle.
Exactly. It's a really elegant and powerful approach to problem solving.
Hmm.
And what's interesting is that this example also shows how observation and even early forms of experimentation were already playing a role in his thinking, even in the rules, which are mostly focused on a priori reasoning. To understand how light behaves when it passes through different materials, you need to actually observe it to experiment a bit.
Right. So even though he's all about clear and distinct ideas and logical reasoning, he also recognizes the importance of empirical observation.
Right, he's not an armchair philosopher who just sits and thinks all day. He goes out and tests his ideas, observes the world, and uses that information to guide his reasoning.
This is really insightful. So we see how his method works in practice, how he breaks down complex problems, uses intuition and deduction to build up knowledge, and incorporates observation and experimentation into the process. Now, later in his career, Descartes wrote a more concise version of his method in the Discourse on Method. How does that version compare to the more elaborate one we find in the rules?
So, in part 2 of the discourse, he gives a more streamlined, more accessible version of his method with just 4 rules. The first rule is basically to never accept anything as true unless you absolutely know it to be true. No hasty judgments, no accepting things on faith. Only believe what you can clearly and distinctly perceive to be true, with no room for doubt.
So rule number 1, the foundational principle, is all about that Cartesian skepticism, that rigorous doubt that leads to certainty.
Exactly. Then the second rule is to divide each problem into as many smaller parts as possible, which, sounds familiar, right? It's like enumeration 2, breaking down complexity into manageable chunks.
Right, divide and conquer. What about rule number 3?
Rule 3 is all about order and logical progression. He says to conduct your thoughts in an orderly fashion, beginning with objects that are simplest and easiest to know, and then gradually ascending step by step to the knowledge of the more complex.
So start with the easy stuff, the things you're certain about, and build from there. Seems like solid advice for anyone trying to learn something new.
Absolutely. And then the final rule, rule number 4, is about completeness and thoroughness. He says to make your enumerations so complete and your reviews so comprehensive that you can be sure you haven't missed anything.
Okay, so don't cut corners, basically. Make
Right.
sure you've considered all the angles.
Right. It's like a reminder to be diligent, to be thorough in your thinking. So these 4 rules in the discourse can be seen as a more practical distillation of the more elaborate framework he laid out in the rules.
It's like he's giving us the executive summary, the key takeaways from his method.
Yeah, exactly. And by this point in his career, he seemed to be more focused on actually using the method to solve real problems than on explaining it in a super detailed way. He even said in a letter that the best way to understand his method was to see it in action, to see how he used it to tackle specific problems.
So theory is good, but practice is even better. Show, don't tell. And speaking of practice, let's talk about the role of experiment and supposition in his method, something that's often overlooked when people talk about Descartes.
Right. People often portray him as a pure rationalist, someone who just sits in his armchair and thinks his way to knowledge. But that's not the whole story. Experimentation actually plays a crucial role in his approach to understanding the natural world, especially as he describes it in Discourse 6 and Principles the Third 4.
Okay, so where does experimentation fit into his system, which seems so focused on a priori reasoning, on starting from clear and distinct ideas?
Well, here's the thing. Descartes believed that the fundamental laws of nature, the most basic principles governing the universe, could be deduced from the nature of God.
God. So we're bringing in theology now.
Well, yeah, for Descartes, God was a crucial part of his philosophical system. He argued that God, as a perfect and immutable being, would have created the world according to certain unchanging laws. And these laws, because they're based on God's nature, don't require any empirical verification. They're just, inherently true.
Okay, so the most fundamental laws of nature are, in a sense, self-evident for him because they're based on the nature of God. But what about when we move from those general laws to understanding specific phenomena, like why does the apple fall from the tree?
That's where experimentation comes in. You see, the fundamental laws of nature might be universal, but they're also really general. They don't tell us the specifics of how things actually work in the real world. They don't tell us why the apple falls, but only that it must fall according to some law.
So the laws tell us what happens, but not how it happens.
Exactly. And Descartes realized that in many cases, a single observable effect could be explained by multiple different hypotheses. So how do you figure out which hypothesis is correct? That's where observation and experimentation come in. They allow us to test our ideas against the real world to see which explanations actually hold up.
So it's about narrowing down the possibilities, using empirical evidence to guide our reasoning.
Right. He describes it as a kind of reverse deduction. We start with the observed effects, then use experiments to isolate and manipulate those effects, and finally, we formulate hypotheses about the underlying causes.
So we observe what happens, then we try to figure out why it happens.
Exactly. And these hypotheses often involve what he called suppositions, essentially. Educated guesses about things we can't directly observe, like the shapes and sizes and motions of the tiny particles he believed made up matter.
So it's like we're using observation to infer the unseen.
Right. And crucially, Descartes believed that these suppositions, even though they were based on observation, could ultimately be deduced from those first principles, from those fundamental truths about God and the nature of reality. This is a key difference from a purely empirical approach, where hypotheses are confirmed solely through repeated testing. For Descartes, experimentation serves to guide and structure the process of deduction, not to replace it.
So experimentation, for him, is a tool for refining our deductive reasoning, for helping us apply those general laws to the specific complexities of the natural world.
Exactly. It's about using observation and experiment to help us figure out how the world actually works, based on those fundamental principles we know to be true.
This is really helpful for understanding how Descartes' method works in practice. And to see it in action even more concretely, let's look at some specific examples. The source mentions his work on optics, especially his discovery of the law of refraction.
Right, the law of refraction. That's a great example of how he combined observation, experimentation, and deductive reasoning. He starts with some insightful analogies, like comparing light to a blind man's stick to illustrate its instantaneous transmission. And then he uses the analogy of wine flowing in a vat to explain how light tends to move in a straight line.
And of course, the famous analogy of the tennis ball hitting a stretched sheet to explain how light bends when it passes from one medium to another.
Yeah, that's a classic. And by carefully analyzing this analogy, by breaking down the components of motion and seeing how they're affected by the sheet, he was able to deduce the precise mathematical relationship between the angle of incidence and the angle of refraction, which is now known as Snell's law, or the law of refraction.
So he's using these everyday examples, these relatable analogies, to help us understand something as abstract and complex as the behavior of light.
Exactly. He's making the complex simple, which is a hallmark of a great thinker.
Absolutely. And another example highlighted in the source is his work on meteorology, specifically his explanation of the rainbow. Now that seems like a really complex phenomenon to tackle using his method. How did he approach that?
He did, and he considered his explanation of the rainbow to be a real showcase for his method. Like, look at what my method can do. So he started by carefully observing all the features of rainbows, when they appear, where they appear in the sky, the order of the colors, the presence of primary and secondary bows, all that stuff. And he even used a physical model, a big flask filled with water, to study how sunlight interacts with individual water droplets.
So he's going from general observations in nature to more controlled experiments in the lab.
Right. And he carefully tracked the angles at which different colors of light appeared in his flask relative to the incoming sunlight and his position as the observer. And then he started manipulating his setup, blocking certain rays of light, allowing others to pass through, really trying to isolate the key optical processes at play.
So he's like a detective trying to piece together the clues.
Exactly. And what he found through his experiments was that the curved shape of the water droplet wasn't actually essential for the separation of light into colors, nor was the process of reflection. The key factor was refraction, the bending of light as it entered and exited the water.
And he compared his findings from the flask experiment with observations of light passing through a prism, right?
Yeah, which is important because a prism separates light into colors without any reflection from a curved surface. This helped him to isolate the role of refraction and to see that the shadow, or the limitation of the light's path, was also a crucial factor in producing the colors. And this led him to more micromechanical explanations, considering the nature of light as composed of tiny rotating particles and how their rotation might be affected by refraction.
Wow, so he's moving between these different levels of analysis, from macroscopic observations to microscopic explanations, all while using his method to guide his reasoning.
Precisely. He's integrating observation, experimentation, and theoretical reasoning to arrive at a really comprehensive explanation for a complex phenomenon.
It's a beautiful example of his method in action. Now, let's turn our attention to mathematics. The source mentions his work on geometry as a key demonstration of his method's power.
Right, so in geometry, Descartes wanted to show how his method could be applied to solving problems in mathematics, specifically geometrical problems. And he chose geometry because it represented what he called perfectly understood problems, problems where all the necessary conditions are clearly defined within the problem itself.
Okay, so unlike those messy problems in natural philosophy, geometry is nice and clean, logically speaking.
Exactly. And his big goal in geometry was to demonstrate that all geometrical problems could be reduced to finding the lengths of straight lines and then performing basic arithmetic operations on those lengths.
So simplifying geometry down to its most basic elements, and why was that important to him?
Well, one reason was that he wanted to overcome a long-standing limitation in classical geometry, known as the problem of dimensionality.
Problem of dimensionality. That sounds intriguing. What was that all about?
Basically, the issue was that in traditional Euclidean geometry, you could represent a numerical quantity as the length of a line, the square of that quantity as the area of a square, the cube as the volume of a cube, and so on. But representing higher powers geometrically became tricky because physical space, as we know it, only has 3 dimensions.
Right, so you can have a line, a square, a cube, but what about a four-dimensional shape?
Exactly. And this limitation made it difficult to apply algebraic methods to solving geometrical problems. So Descartes' brilliant solution was to show how you could represent all those higher powers as lengths of lines without ever needing to go beyond those 3 dimensions. He used the concept of similar triangles and proportionality to show how multiplying two lines together could be represented geometrically as another line.
So he's basically breaking down this dimensional barrier, showing that you can do all your math with just lines.
Exactly, and this was a huge breakthrough. It paved the way for analytic geometry, which combines algebra and geometry in a really powerful way.
And how did he actually apply his method to solving specific geometrical problems within geometry? Expert speaker.